Okay, so first of all, Difto Musma, that means hello in the Vulcan language, as we really don't know when you are all. And welcome to the Infrastructure Control System session. My name is Stéphane Perez, I'm from CEA, and I will co-chair this session with Alain Buteau from Saint-Contraux-Soleil. So we will have 4 talks in this track with 12 minutes speech, 3 minutes for questions, and we will inform the speaker 2 minutes before the end of the talk. So Alain, you can introduce the speaker.
Sorry. So the first talk will be done by Benjamin Bertrand from Max4. He will speak up of control system management and deployment at Max4. So Benjamin, it's up to you.
Okay, so let me share my screen. Yeah, thank you for the introductions and hello to everyone. So today I would like to give you an overview of how we deploy, we package and deploy software at Max4. So I have a lot of things to cover, so I will go quite fast, but I will be happy to go more into details and answer questions later. So we should start with a short introduction, then speak about packaging with RPM and Conda, and then we'll finish with a deployment with Ansible. So first, to give you some context, Max4 is a synchrotron facility. We have 16 beam lines. The control system is based on Tango, and we have hundreds of virtual and physical machines that we have to maintain and where we deploy software. So the control system is made of many different components that have dependency with each other. It's not straightforward to build and deploy individual software without breaking another part. And this is why early on, Max4 decided to use RPM to package software on Ansible for deployment. So we start with RPM. So RPM is the Red Hat Package Manager. If I change to RPM Package Manager now, the name. It's a well-known package manager that is used on several Linux distributions, including CentOS, which we are using at Max4. So it was an obvious choice as a package manager because it provides a large number of high-quality packages, so it's a solid foundation to build on. So to build a RPM package, usually what you need is a spec file, which looks like that, and that's how you can define the dependency you want to have in your package at build time and runtime, and the different steps to build your package, the file you want to include. So spec files, that's what we use for C++ projects. And to do that, we have a GitLab CI template that developers just have to include in their project. And this template basically will run this max package command, which is just a plugin for R package, a tool to build RPM from the Git repository. And the pipeline will build the RPM and publish both the source and binary RPM to our repository. So at Max4, we have a lot of Python. And so for Python, the historical way to package is to use setup tools and setup.py. And in setup.py, usually you use install requires to define your dependency. And so we could write spec file as well, but so we chose to use FPM, which is a tool to build platform native package. So FPM, it takes several sources, and Python is one of them, is one we are interested in. And it takes as well a target. So it could be a Debian package, but so we want to build RPM. So it's RPM. After you have other flags that are not that important here, but with such a command, basically, with a previous example, it's how you can build a RPM. And it will take information basically from the setup.py, and so the requirement that you had specified, they will be translated to the RPM naming convention. And to build this RPM, basically it's the same. We have a Python CI template for our GitLab CI pipeline. And in this template, that's what will run the FPM command, so with different flags. So the developers, they don't really have to care about that. There are some variables they can provide to tweak some things, but this template basically will build the RPM. We build as well the Python package because it can be useful for development, run some tests, and then we publish both, so the Python package and the RPM to our repository. So this has been working quite well and it's still working well. But so RPM is really tied to the operating system release cycle. And especially with the decision of the CentOS project to shift focus to CentOS Stream, we stopped our migration to CentOS 8 and we stayed on CentOS 7. And this started to create some issue to install newer software because, yes, CentOS 7 is quite stable, but so there are some dependencies that were not available. So this is why we started to look at some alternative to package our software, and especially Conda, which is well known in the Python world and data science world especially. So Conda is a package manager, which is not just for Python, it's for any language. And it has some nice features, so like creating isolated environments, so you are sure you're not gonna break something in the machine. It's OS independent as well, and there are many packages available on Conda Forge, especially for Python. So first, to be able to use Conda, we needed a server to host our package, and so we deployed Quetz, which is a fairly new project, but it allows us to have local channels to upload and store our internal software, but we can proxy and mirror as well external channels like Conda Forge. One thing I would like to speak about is Conda performances, because that's sometimes a complaint that you hear about Conda, that it be quite slow to solve environment, and it's kind of true when you use a big channel like Conda Forge. So if we take this example of Sardana, which is a well-known framework in the Tango world, you see that just this environment, it takes almost more than 35 seconds to just solve the environments and more than almost 1.2 gig of RAM. So this was kind of an issue, but fortunately there are solutions to that. And one of them is Mamba. Mamba is a drop-in replacement for Conda with some parts we implemented in C++. And as you can see, so for the same environment, it takes less than a second to solve it and 10 times less RAM. So Mamba is great. I really recommend you to use it. But it was not really enough we couldn't rely just on it for all our use cases. So what we did as well is to create a mini Conda Forge channel, which is just a local channel with just a subset of the Conda Forge package that we are interested in, because we really don't need the whole Conda Forge channel. And with this channel, you see that solving the same environment takes just a bit more of 1 second with Conda and less than 50 meg of RAM. So there's a really big boost of performances. Really, Conda performance really depend on the size of your channel. And with Mamba, it's of course even faster, but the difference in this case so is not that important. So, and to maintain this channel, basically, we just have a text file in a Git repository where we list all the environment we want to be able to deploy in productions. And we have a script that is run in a GitLab CI pipeline on schedule that will download the package and all their dependencies and upload them to our mini Conda Forge channel. So quickly to speak about how to build a Conda package, you need a recipe. So this is a typical recipe for a pure Python package on Conda Forge. So usually you take the source from PyPI. This is the same, you define your requirements. So it's a bit like the spec file for RPM. And so for Conda Forge, there's a specific repository, and we use it for some package that we want to contribute to the community. But so for internal software, we didn't want to have a separate repository to maintain. So we put the recipe in the same, in the source repository, basically. So you see that the source here is the parent directory. There's a recipe directory with a meta.yaml file. And we use as well some macro provided by Conda build that makes it easy to take information from the setup.py, like the version and the requirements. This makes it quite easy to maintain the recipe, and we even have some cookie cutter template to create those recipes. And for building the package itself, in fact, we use exactly the same Python CI as before, and we just added a stage that only runs if recipe.meta.yaml file exists. And that one will run the Conda build command to build the Conda package. And we can still build in parallel RPM, but sometimes if there are dependency missing in RPM, it doesn't make any sense. So you can disable the RPM build with this variable. And basically, so this pipeline will build the Conda package, the Python package, run the tests as before, and publish the package to our repository. So this was for the packaging part. So now after we need to deploy those packages to all our machines. So we use Ansible for that. So for RPM, it's quite straightforward because there's a yum module in Ansible. But to make things consistent, what we did is to have a specific deploy playbook. And in our inventory, in the old file, basically, we define all the RPM we have with the latest version available. And then on each host or group of hosts, we use this package table variable where we list the package we want to deploy to this specific machine. But you can use then this default value that will refer to the version that is in this file. So it makes things very consistent, and you don't have to modify many files after. When we bump the version of the package, we can redeploy on many hosts at the same time. But sometimes it's needed, you can still pin to a specific version. For Conda, there's no built-in support in Ansible, so we created
2 minutes left.
Thank you. Yeah, that's okay. We have created some custom modules. Actually, it's based on the modules I created while I was at ESS, and we have two modules. We have a Conda module to work with Conda packages, and a Conda env module to work with environment.yaml file. And so what we have a Conda role, which by default will deploy and configure both Conda and Mamba, but you can define as well some environment variable. So with this Conda env, you can define a list of environment that will be automatically created or updated by the role. But as you see, we define as well these wrappers, and this is because by nature, Conda environment, they are isolated from the system. Usually you need to activate an environment to use it, but we want it to be transparent for the user. So what we do is we create this small script under user local bin that will just activate the environment and run the command. So it means that the user doesn't have to know that the tool was installed in a Conda environment or RPM. It will just run the command and it will just work. And for Sardana that I mentioned before, so we have the environment is a bit more complex. So we have a specific role for that. But basically we'll create an environment.yaml file that can be customized based on some variables. And then it will use this Conda env module to create the environments. And we do that because using environment.yaml file, you can mix both Conda packages, but as well pip packages. For sometimes if we don't have Conda package yet, you can mix both. So that's why we used this environment file. And that's basically it about what I wanted to say already. For modern software development, I think, and to manage dependency, I really recommend using a package manager, as we saw. So each package manager has its strengths and weaknesses. But when we combine that with Ansible, in our case, that really gives us a reliable and reproducible way to deploy our software. So thank you. And if you have questions.
Thank you.
So I will relay one question from Alessandro Silenzi. Do all packages use the same version of a base dependency, for example, Tango?
Yes. So Tango now, there's package on the. If you speak about RPM or Conda, it depends. But yes, usually we try to push when there's a new version of Tango. We create actually the RPM and we try to deploy that on all the beamlines. And depending on the version of the update, sometimes you have to rebuild the RPM package if there's it's not ABI compatible, but if it's ABI compatible, we don't have to do that. And Conda is basically the same. For Conda, it was quite recently, so it's all the package were using the latest version of Tango, because now Tango package are on Conda Forge.
So as a question, maybe one related to Conda, what is the risk as Conda is maybe considered as a third-party software?
Conda itself, it's an open source project, so it's like many it's Anaconda, the company which is behind Conda.
The question was related towards the shift of Conda towards commercial license.
Yeah, but so this actually it's really concern just the Anaconda default channels and the Anaconda distribution. So if you use Conda itself, the package manager, this one is completely open source. And if you use other channels than the Anaconda default, like Conda Forge, there are no, I know they change their TOS, sorry, the term of use, yes, but so the term of use, they really apply just to the Anaconda default channels and the Anaconda distribution. They don't apply to the Conda Forge channel, for example, which is completely free and open.
Okay, and the last question, which may do the transition with the next talks, is have you considered containers instead of Conda?
Yes, actually, we use containers, for example, for web applications and sometimes, but containers for graphical application doesn't work. There's Singularity actually that we tried for to deploy Sardana, but for us it was just another layer that was added because inside Singularity we are still using Conda to install the package. So that's why for this use case we thought Conda directly was easier.
Okay, thank you. Maybe Stéphane can move to this next speaker, and thank you, Benjamin, again. So okay. Stéphane.
Thank you very much. Next speaker is Chuchang Shen from the ALMA Observatory. Chuchang Shen is an electrical engineer with a degree of Master of Science in Automatic Control. He has 15 years of experience working in radio astronomy and optical observatories environments. Currently, is managing a team of system engineers, operation planners, and technical leads in the engineering service group of the Department of Engineering of the ALMA Observatory. So, Chuchang Shen, we've explained the capability of FRCAT as an alternative or real-time control system for ALMA. So I give you the stage. Okay.
I will share my screen. Can you hear me well?
Yeah.
Perfect.
Okay.
Yeah. Presentation mode. Okay, and thank you for the kind introduction, Stefan. Well, so today I'm going to talk about the different alternatives that we have evaluate in order to solve the obsolescence problem that we have in ALMA. And so for those you is not familiar with ALMA, ALMA is a radio astronomy observatory and installed in the north of Chile, in the desert of Atacama Desert. And this is a picture of most of the antennas. We have 66 in total in the Chacnator Valley, which is 5,000 meters over the sea. So as I said, we started to operate since 2013. After 8 years, we started suffering for the obsolescence problem. And one of the main problem that we are trying to mitigate is the antenna control bus. So in the left, you can see the diagram. In each antenna, inside of each antenna, there's a real-time computer that we call antenna bus master. This computer has to control all the low-level control of the hardware devices that instead controlling the different subsystems, such as pointing of the antenna, digitizing of the signal, control of the receiver, digitalization, and data transmission. And all this has been coordinated with a cluster, centralized cluster, in coordination with all the array, the 66 antenna. So just for this real-time computer, we have 66, one for each antenna. And in the other centralized location, we're using the same real-time computer for control. So we have around 80 computers that's obsolete. We cannot find more spare for the following years. So that's the reason we start looking for alternative. And in order for the ABN to control the hardware devices, there's a standard device that we defined for each hardware. And this is made by, we call AMSI, it's an Animal Monitor and Control Bus Standard Interface. And it's based on a ST microcontroller with a CAN bus transceiver. And this is the way the PCB looks like. So as I said before, in order, the avian is here from the software point of view. The avian is here and he send the control message using SES. And the logic is embedded inside of what we call hardware device components as a piece of software. And using RTI, we make sure that this is real time. And through the kernel modules, we translate those messages to the CAN bus. The message arrives to the AMSI, and internally, the AMSI interact with the final hardware using SPI, using I2C or other kind of electronic protocol. So for this research, we will apply for funding. ANIT is a Chilean national investigation and development agency. We apply for a funding called KIMAL, and we received 200 million pesos, which is equivalent to $250,000 US for a period of 2 years. So we did a quick analysis with the different alternative that we have, and since we are already using CAN bus, it's very easy to check to see that EtherCAS is the one possible replacement of CAN bus. There's a lot of compatibility within both standard, and the advantage is the limit of nodes is now 65,000, which is almost infinity for what we need. And the cabling, the media is Ethernet cables, which is make the installation easier. So this is a new architecture that we presented. It's driven by the different scenario that's coming for us. So we still have you.
Does it work for you? We can hear you.
The sound was pretty bad, Stefan.
Yeah.
For me, at least. But I think we lost the speaker. Yeah, to the sound loop.
You're right.
And we lost the speaker.
Yeah. He doesn't know we can hear him. I will send him a message. Is he disconnected or not?
I know where to know. I still see the slides, Stefan, but
we ask for help to this stuff.
Otherwise, what we can do is to move to the next speaker, hoping that he will be able to connect again next. Maybe we can go to the presentation of Rémi. What do you think, Stefan? I do not hear you, Stefan.
Can you hear me?
Yeah, okay, that's fine.
Yeah, okay, it's okay. You can go through.
So maybe Rémi, Rémi, are you ready?
I'm ready.
Okay, I will introduce your speak, please. So Rémi Voirin is a computing infrastructure manager, engineer, in CERN Accelerator Controls. After completing his master's studies in network and telecommunication at the University of Savoie, he began his career as Unix system administrator at Infomaniac, a Swiss web hosting company. And he joined CERN in 2017 to participate in the renovation of infrastructure monitoring. And now he takes care of the current operating system on front-end computers and leads the container projects for controls. So Remy, it's up to you. You have 12 minutes.
Okay, let's share. Okay, all right.
We still see the slides from Alma.
Yeah, apologies. I was just minimizing the squares. Okay, all good now?
Not yet.
Okay, can you see the blue CERN screen?
No.
No, I still see it.
So on the previous presenter screens.
Yeah.
You still see the other presenter screen?
Yeah, maybe I can stop.
Okay,
Yeah.
okay.
Yeah,
that's fine now.
Please.
You got the line.
Oh, okay. Okay, what about now? Do you see my screen?
Yeah.
Yes.
Okay, and do you see
okay, perfect.
Main title? All right, okay. Thank you, Alain, for the introduction. Hello and welcome to the State of Containerization in CERN Accelerator Controls. This presentation is a follow-up of the Containers and Controls workshop that took place during the last iteration of ICALEPCS. This was a full-day workshop with 30 attendees, 6 presentations, 2 group work sessions, and 3 hands-on exercises. There will be 3 parts in this presentation. I will start with a technical overview of containers. Then I will talk about what we've done since 2019, and finally about our future plans. So a bit of technical background first. As you can see in this diagram, an application and its dependencies run in a containerized fashion. They are separated from the operating system and init by a containerization layer, which provides isolation on multiple levels. So file system, process table, network, and others. And this is all thanks to the Linux kernel namespaces. The Open Container Initiative provides specifications related to how a container is stored and then run. In industry, containers are used for running containers in different environments. Let's say you can run your application exactly the same way on an Ubuntu laptop and on the production CentOS server. As you can wipe and recreate your containerized environments at will, they help streamlining the use of DevOps tools, particularly CI/CD. As you need to embed your dependencies in your container, you need to manage them properly. So containerization helps you with it. And finally, even if security-wise this is not a good idea, you can have your legacy application as a black box and carry it through the ages in a container. So since 2019, we have started the container project, which purpose is to offer the ability to run containers on our disk-based systems, so servers and technical consoles. And to do this, we need 3 things. First, a set of base images in order for our developers to package the applications. Then a registry to store these images. And finally, a container engine, which is a piece of software to run these containers on these disk-based hosts. So let's talk about the base image. And actually, there are 4 steps to create it. First of all, we set up a few base CentOS packages in a subdirectory using yum or DNF. We inject a few custom configuration files, GPG keys, extra yum repositories. We create a tar archive out of it, and we convert this tar archive to the OCI format. We recreate the base images every day using a GitLab CI pipeline. It helps us catching any error with new versions of packages or the Java environment. For the registry, there is an approval mechanism that is detailed in extra slides and also in the paper. So from the list of allowed images in the controls environment, we take these images and we put them into a Harbor instance that is deployed by our colleagues from the IT department. One of the neat features about Harbor is that it embeds vulnerability scanning thanks to Trevi. So it helps us catching any security issue with containers in the controls environment. For the engine, we selected Podman for various reasons. First of all, Podman helps us treating containers exactly the same way as ordinary controls applications. We just have to declare the container in the controls configuration database, and then in a single command, we can instantiate this container on the control server. With Podman, we have rootless containers, which is good for security. So let's say there is a bad scenario here. The application breaks its isolation mechanisms. And in the end, if you are in the user environment and not in the root environment, the attack surface will be thinner. So increased security. Daemonless architecture, it means that there is no extra process running on this disk-based host. And finally, it's also a community-driven project, also backed by Red Hat. So we don't expect any major change in the way it's developed and provided. So we have a few use cases already at CERN. First of all, we have figured that companies deliver their software in a containerized fashion. It's the case for Source Graph that we use to index our code. It's also the case for the Nexus repository manager from Sonatype. We'll use containers to decouple software upgrades from operating system upgrades. We use currently WinCCOA 3.16 to control SCADA systems. And we know that this version won't run on RHEL 8 or CentOS Stream 8. So once we have upgraded the technical consoles, we'll still be able to run WinCCOA 3.16 thanks to CentOS 7 containers. We have applications that have similar pipelines and containers at the end. So for testing, staging, and production, it is the case, for instance, for the LHC injector chain timing sequence manager. And we have also the possibility to give a replica of a complex system for local execution. And this is done, for instance, for the LHC orbit feedback, where no test bench is present in the data center anymore. The software team just provides a container for tests on laptops, for instance. So what about our future plans then? To be honest, we delivered quickly these three components in order to unblock our users with their specific use cases or local use cases. In the meantime, we wanted to provide tooling around containers, and we wanted to enforce security guidelines with container deployment. So now the questions are, should we push for global use of these containers? We are wondering about the added value for all the controls projects. The second question is about orchestration. Should we go for it? And to answer this question, we'll have to dive a bit more into orchestration itself and what it is. So with an orchestrator, you don't abstract a computer, you abstract an entire computing infrastructure. There is the orchestrator that will take care of the scheduling, placing, load balancing, providing an API, and providing also health monitoring for all the containerized deployments. In this diagram, we have two containerized applications with three replicas in this orchestrated environment, namely my app and other app. And when a user sends a TCP request to my app, it will go through the load balancer that will select one of the active my app containers. Actually, we could benefit from orchestration. When we look at the data center today, we have a strong mapping between one project or team and one bare metal server. The end result is we have plenty of bare metal servers, and a lot of them really sit idle. So what we could do is we could densify the use thanks to orchestration. Here we can see that we put 5 teams or projects on one bare metal server, and we still keep a reasonable usage threshold, up to 30%. For free or almost, we get data center redundancy. And so thanks to orchestration. And as you can see in this picture, in the end, we have 4 bare metal servers, whereas before we had 10. So that's a lot of gain on that side. For maintenance windows, it's also better. Let's say we need to replace the server that is in red. In that case, we'll be able to spread the workload of the servers in the data center. And when the hardware replacement is done, we put the workload back. One important point is that if it was a monolithic application, then you get 2 very short disruptions. If you had your deployment in a microservice way, then you get 0 downtime.
Remy, you've got 2 minutes.
All right, thank you. So also with this model, we can move away from the Linux shell interface. We give an API instead. It provides more security by design because you can do less with an API. But actually, it's what our developers want, or some of them at least, because it's easier. They don't have to fiddle with the Linux shell anymore. We have some use cases that are ready, and there were 2 previous talks this week at ICALEPCS that I will let you check out. So is orchestration a silver bullet though? If you have a monolith, then it might be easier to go for virtualization instead. They won't get all the goodness from orchestration, and you have to rethink about the deployment strategy. An orchestrator adds complexity, so it means more risk because it's an additional layer. It requires more human resources to manage it. And that's exactly for this reason that we dismissed Kubernetes 2 years ago already. You also have to think about orchestrator maintenance. Is it transparent? Does it add to your maintenance window? So our next step in CERN controls is to try Nomad, which is a bit of a hybrid solution, managing orchestration and virtualization. So to conclude, we've seen that containers offer advantages in controls environments. We have the 3 bricks of plain containerization that are available, and we are asking ourselves if we should go for containerization for everything and even orchestration. We'd be happy to hear about your thoughts on the infrastructure side. And thank you very much for your attention.
Okay, thank you, Remy. So we have one question from Mikhail Falowski. Have you got problems with efficiency when running containers in Podman as request?
Efficiency, yeah, okay. So we've not hit any issue, but we know that the C group implementation in CentOS 7 can have performance issues. So we'll look into it, but the use cases that we are containerizing right now, they don't take so much on the performance side yet. So we have not hit this barrier yet. So we can keep in touch and yeah, let's share on this topic. It's really interesting.
Thank you, Remy.
Maybe just a question, another question, maybe can you develop the sentence regarding the difference between virtualization and containerization? I mean the load balancing you presented through your orchestrator could be also managed by hyper-converged solutions, for example, and maybe in some automatic way by VMware solutions or whatever.
Yeah, in the second part, I really developed I would say, data center flexibility. And in the end, you can get some of the data center flexibility with virtualization. So yeah, there is really this question about whether we should go for 100% orchestration or if virtualization also makes sense. We have plenty of ways to deal with this. But yeah, okay, you can get some of the goodness already with virtualization. What you get with orchestration is really the API side. and some more flexibility. I would say it's lightweight because you don't have an additional kernel. So yeah, you have to weigh pros and cons between virtualization and orchestration. It's not black and white.
Okay.
It's all I can say in a few seconds. Yeah.
Okay. Maybe we can discuss later. Okay, thank you, Remy.
There is one more question. Maybe I don't know if we have time for this question from Matteo Di Carlo, who didn't understand what's the orchestrator he's using. If not, Kate.
Okay,
Not
can you
Kubernetes,
repeat?
or-
Okay, so
okay.
can you?
Which? Yeah.
Okay. Yeah. If not, so we are looking at orchestrators. So yeah, it's a bit generic, but Kubernetes is not the only one out there. So you have plenty of Kubernetes distributions out there. You have, of course, you have OpenShift, which is a big one, but you have Rancher. Okay, some other products as well. But Nomad is one of them, and it does not provide the Kubernetes API. So the ecosystem is getting bigger and bigger, and the array of choices is quite large. To me, the question is not just about Kubernetes or no Kubernetes. And when I say that we dismissed Kubernetes, it's self-managed, as in we have to manage the distribution itself. Maybe we can go for Kubernetes, but something that is already nicely packaged, I would say, and something maintainable in the context of the controls environment.
Okay. Thank you,
Thank
Remy.
you. Maybe we can try again with Suchang. Are you here?
Yes, can you hear me?
Oh, okay, great. We should try disconnecting your video during your presentation. Maybe it helped. And I think you can go to the third one. Can we see the?
Yeah, I'm sharing.
I don't know when it blocked. 5, 6. Can you go through this? I'll tell you the. Okay, go again. Okay, we had this one. Okay. I think it's stopped. Okay, again.
Next one, yeah.
Next one. Okay, it stopped here, I think.
Okay. And I think you have something like 7 minutes left, or Stefano?
Okay.
I don't remember. It should be, yeah.
Okay, whatever.
Okay.
I try my best. Okay, so this new architecture that we define is very driven by the coming situation or coming the scenario that we expect for Alma. So the scenario 2 is the existing obsolescence problem in the control system, control bus, and eventual new other subsystem that has obsolescence problem, but they will continue using AMSI as the main interface to the control bus. Okay, and since we are doing improvement in antenna recovery due to bad weather, and so we are adding a lot of commercial off-the-shelf digital I/O, analog I/O, and whatever modules, and this can be used native EtherCAT protocol and using this EtherCAT coupler. This is the scenario 3. And for ALMA has defined this roadmap for ALMA 2030, in which we will upgrade a lot of hardware inside of the antenna and in the central processing system. And we don't know which protocol we are going to use and be used, but EtherCAT could be a good alternative to set up the framework that this new system can be designed. Instead of designing something that they don't know yet, having a framework or a standard will simplify both parties. And the use case number 5 is just generalization of the other cases. So if another subsystem or another big system have a proprietary bus, we can also interface that, developing a specific EtherCAT coupler. And one aspect which is also important, and the ABN, we have split in 2 sections. And the top here, which is using SES, will become not real-time. And the EtherCAT master will do all the real-time aspect. That's important because we decouple this, the access to the monitor and control bus. So electronic engineer, they can access to the antenna, while the software engineer, they are doing maintenance in the software, restarting the container, whatever. For the time being, we cannot do that. We always rely in ALMA software and to access to the control bus. Okay, so the setup that we did is very simple. So we have a laptop, a very powerful laptop with two virtual machines, one with ACS and another with Windows plus TwinCat 3 to develop the code that's run inside of backup master, EtherCAT master. CX2030 is the model that we're using, and the EtherCAT node, the slave, is based on Infineon XMC4800 microcontroller. And this will interface to the AMSI board. So this is the setup. So this area of communication, we have Ethernet, here we have EtherCAT, and here we have Canvas. So the message flow is like this. So from a user can send an OPC UA message to the EtherCAT master. And EtherCAT master will translate the message to EtherCAT message. We reach to the XMC4800, and this will translate again to Canvas. And then we'll talk to an AMSI device as usual, and the response will follow the same way back. So going in detail, one important aspect of synchronization in ALMA is we have this concept of timing event that allow us to synchronize all the different antennas or different hardware real-time computer. So a TE is just a digital pulse of 48 milliseconds. In the first windows of 24 milliseconds, we're supposed to send only control messages, and the remaining 20 milliseconds we are allowed to send monitoring messages. And there's an idle period of 4 milliseconds, and then we repeat again and again. So for the EtherCAT master portion of this data flow, so we receive in the diagram in the bottom, you can see we receive from the OPC UA server the request, and the dispatch command will split in two queues, the control command and monitor command. And here we make sure we are fulfilling this requirement of TE. So and the data will be encapsulated in using SDO, a service data object, and the information we put in the Ethernet cable, EtherCAT message to the slave. The second portion of the data flow is inside of XMC4800, and we received from the EtherCAT master the EtherCAT message. We open this data structure and convert into CAM message and send it to the AMSI. Okay, so we did some performance experiments. So we sent 10,000 message and defined the object directory. This is a very simple device, just have 6 sub-indexes. And we're using Wireshark in order to, as a sniffer, in order to see the time of fly of each package. And as you can see, it's quite deterministic. So we can, one type of message is taking 200 microseconds. Another type of message is taking 400 microseconds. This is because of the implementation in the AMSI itself, not in the protocol of EtherCAT. So the conclusion on future works. So we demonstrate that we can use this commercial off-the-shelf hardware and as an alternative to replace or to solve the obsolescence problem in the existing real-time computer. We demonstrate that EtherCAT is a suitable protocol to replace the existing field bus in ALMA, and which is based on the customized version of CAM protocol. So for the time being, we only experimented with SDO structure, service data object, but we think if we try with a process data object, we will allow more performance. This is under investigation now. And the architecture that we define is fulfill the different scenarios that ALMA is expect to face in the coming years. And we also found that XMC4800 is very versatile microcontroller, and mainly because it is one of the few microcontrollers that can allow multi-CAN interfaces. Most of them has 1 or 2, but we need 5, so that's very convenient for us. But we also want to test other EtherCAT slave controllers like Texas Instruments, Citara processor, AM635X, or microchip equivalent. Okay, so that's the information I would like, I want to share, and thank you for listening to me. And if you have any other experience in this area, we are very happy to share our results.
Thank you very much for this very interesting talk on the real-time systems. I don't have any question from the audience. I just have one. Do you have any link with SKA regarding this kind of system or not? Or is it really completely different?
Maybe I don't get the question. Link to what?
Okay. Do you speak with SKA telescope system, and do you know they have the same kind of interrogation or working the same kind of system? Yeah.
We have, personally, I participate in several PDR review of SKA, so I know several of them, but they are using Ethernet-based approach, not using field bus. So they are pushing, but I think you're right. Maybe that is a couple years ago, so maybe I have to check again. So maybe we can combine the effort.
Okay, thank you. No other question? I can hear you, Alain. Your micro is not connected.
Sorry,
Alain?
I was muted.
Okay.
Maybe you have to move to the next speaker, Stefan. I don't know if we are late or not. But...
Okay, so with technical problems. Okay, next speaker is Gilles Knapp.
Thank you.
Thank you again, Su-Cheng. Sorry for the problems, technical problems.
Nothing on this kind of work. Thank you.
Okay, so Gilles Knapp is from Diamond. He has 20 years experience in business software development, working at HP and Microsoft. For the last 10 years, he had switched to science and has been implementing control systems for Diamond Light Source. And he's passionate on open source and fond of Python, Kubernetes, and EPICs. He will have a talk on the use of Kubernetes for EPIC IOCs. You got the line.
Thank you, Stefan. Good day, everybody. Recently, Diamond Light Source has been investigating how we might build, deploy, and manage our EPICs IOCs in the future. And I've built a working proof of concept, which I'm going to present here. So for this project, we've taken the best ideas from modern cloud native applications. The service architecture of EPICs IOCs really lends itself to this. So there are 5 main themes to the project. First, containers give us a way to package up EPICs IOCs and their dependencies. Second, Kubernetes supplies the runtime and management of those containerized IOCs. Third, Helm gives us a way to create EPICs IOC packages to deploy into Kubernetes. Fourth, the source code and other assets are all kept in repos, meaning we do not need a shared file system for distributing code. And finally, continuous integration allows us to generate the above assets from their source as we check the source in. So the first of our 5 themes is containers. Remy did a reasonable job of introducing you to containers, but my simplistic take on it is that containers provide a simple function, a similar function to virtual machines, in that they provide a self-contained isolated unit for your software and its dependencies. But they do so in a much more lightweight fashion because the abstraction is at the OS layer rather than at the hardware layer. So all containers are sharing the host's kernel. And a container image is the virtual file system that's used to bootstrap a container by mounting it at runtime. There are many registries that hold useful predefined container images, such as the best known being Docker Hub. But for this project, we've added our own image registry to hold our EPICs IOCs and hosted that on GitHub. So an important subtlety of our approach is that our EPICs IOC images are generic. That is, they contain binary and libraries needed to talk to a particular device, but they don't contain anything specific, no startup scripts or databases. So with this approach, we only have 1 image per class of device. And then IOC instances are created by launching that generic image into a container and adding just a startup script to define the unique properties of the instance. Note that there's a layered architecture to the virtual file systems that containers hold, and each of these layers is shared and therefore minimizes the disk space and memory footprint if you have multiple images sharing those layers on a single server. So the second of our 5 themes is Kubernetes. It's the dominant orchestration platform today for containers. It originates from software built by Google to run their infrastructure, but was open sourced in 2014. And by using Kubernetes, we get a long list of standard features. The screenshot here is of a standard Kubernetes dashboard showing some EPEX IOCs for our P45 test beamline. And from here, I can review the which versions of my IOCs are running on which servers. I can start and stop those IOCs, can see how much resources they're using, and check their status and their logs. So at Diamond, we already had a powerful on-premise Kubernetes cluster called Argus, which contains 20 worker servers and 3 control plane servers. It's a high availability cluster that can tolerate the loss of a control plane or any number of its workers. And for the proof of concept, I've created IOCs for the test beamline P45, and I run them on the Argus cluster. So initially, we were running those IOCs in the worker nodes in the cluster's own racks, but I've discovered some issues with network protocols used by EPEX. Primarily, this is to do with protocols like channel access, which do not transition through a network address translation table into a virtual cluster network. So we switched to a distributed topology with centralized management, with the IOCs running on worker nodes that sit inside each beamline. So we've repurposed the original IOC servers to become remote worker nodes for the Argus cluster. So the containers run in there, they run on the beamline subnet and are granted access, direct access to the network to resolve all of these networking issues. The third theme is Helm, and that's a package manager for Kubernetes applications. I've created a Helm library that shows how to craft up the necessary YAML to instruct Kubernetes to create resources for an IOC instance. We have a beamline resource, a beamline source repository, which defines the set of IOCs for a beamline, and that will generate a Helm chart for each IOC instance. So I'm going to show you an example of this in detail to try and explain the process. So this example shows the various parts coming together to make a running IOC. It's an example motion IOC for P45 test beamline, and it will talk to a Delta Tau PMAC motion controller. So first of all, we have a generic image that contains the necessary code to talk to PMAC controllers, and that happens to be based upon the EPEX modules image, which contains essential support, and in turn the EPEX base image. All 3 images reside in an image repository, and that repository is hosted by us on our EPEX containers GitHub organization. So that's the image side of things. Now onto the specifics of an IOC instance will be described in a Helm chart. And the Helm chart resides in a Helm repository, which is also in the GitHub organization. So the Helm chart describes what image we want to load into our file system. It also adds the text of a startup script. And the startup script provides the specifics of this instance, such as the IP address of the controller it's going to connect to, and what axes that controller has, and what process variables it's going to present on the network to allow you to control those things. Finally, there is a reference to the library I mentioned, the Helm library, which tells it how to construct this YAML to bootstrap these resources. So when I tell Helm to install a specific version of a specific instance of an IOC, it will go and pull that version from the Helm repository, and it will then use that to generate YAML that it applies to the Kubernetes cluster. That will cause it to spin up a deployment, and that will contain a pod which will host a container, and the container goes and pulls its image to bootstrap its file system from this image here. It also maps this config map into its file system, so it can see the startup script we defined in the Helm chart. So once that's all loaded, we can launch the IOC startup script, and that can find all of the binaries, etc., that it needs to run inside of the container. So we now have a running IOC instance in the cluster, and all the assets from this came from repositories. The last two themes of our proof of concept are repositories and CI. We use continuous integration and continuous delivery to generate the built assets and deliver them to their registries. This is both the generic IOC image and the beamline Helm charts that describe the IOC instances. So therefore, our sources are checked and verified every time that they're pushed into the source repo, and an appropriate image or Helm chart is generated and pushed to the repository, to the registries. And there's a tight coupling between the source code version tags and the version tags of those assets. So I've just put this slide up here to review the functionality that's being supplied by Kubernetes and Helm, and it covers all of the day-to-day activities of IOC management. And previously, these features were all supplied by systemd, procserve, a collection of proprietary scripts, and a set of shared file systems. Some of these features were not available in the old world, so managing a failover of a server, so you're moving your IOC when it fails, and controlling the amount of resources the individual IOCs use is a feature that comes from Kubernetes rather than our old system. So the current status of this project is that we have a test beamline running all of its IOCs on a local Kubernetes node managed by our central Kubernetes cluster. And absolutely everything I've used to build this proof of concept is available to look at in the GitHub organization linked here. And there is a reasonable amount of documentation as well. The documentation includes a tutorial that walks you through creating your own mini Kubernetes cluster and deploying a simulated area detector IOC to that cluster. The documentation also includes this presentation and accompanying paper. So please take a look at the organization and contribute your own ideas. So the benefits of using containers are well documented. My favorite outcome of this is that it's allowed me to use vanilla versions of the EPEX base and EPEX support modules. No longer do I need to maintain my own fork of those sources to support our unique infrastructure requirements. This kind of raises the possibility that facilities in future could share container images, and we could do less compiling and more assembling of building blocks. Having centralized management in Kubernetes brings great economy of scale and means we no longer need to maintain our internal tools for deployment and management, nor a separate build server. One thing I've not drawn much attention to in these slides is that the containers also provide a portable environment for testing, debugging, and developing IOCs and support modules. And this means that developers can work anywhere. We can guarantee the developer environment matches the runtime environment. We no longer need to install the toolchain on individual workstations. And all this means that the rollout of new OS releases to workstations and servers becomes much easier because it's completely decoupled from the development environment and the runtime environment. So that is all I had to say. Thanks for listening. And I think we've got the time for questions.
Thank you, Gilles. There is no question in the audience. I have two questions, maybe one small, one more complicated, I don't know. Are you using some kind of digital twin in order to test all your systems?
We are building a simulator of beamlines, which itself runs in containers. But presently, I'm testing this on a real test beamline with real hardware. So I have a couple of cameras and some motors, and it's not actually, it doesn't take X-rays, it uses visible light, but it does have many of the elements of a real beamline, and that's what I'm testing this with.
Okay, thank you. There is one question from the audience. Could you expand a bit on the network issues that you encountered that caused you to push the Kubernetes containers closer to the beamline?
Yes, so the primary communication mechanism between a EPEX IOC and the graphical clients that we use for operator interfaces and for other applications is channel access and PV access. Both of those protocols use a broadcast to find the EPCS IOC that serves the PV it's looking for. And one of those IOCs, in theory, only one IOC is then supposed to respond, and they set up a channel, and the client and the server set up a channel. That broadcast will not travel through into the virtual network that you would have if you had your pod in a traditional Kubernetes virtual network. I looked at all sorts of solutions to this, and I did come up with a way of making it work, but I then also found problems with the Gigi camera streaming protocol that was quite similar, because the protocol passes port numbers, ephemeral port numbers, and IP addresses inside the application layer, and also breaks any NATs. I realized that I was going to need to fix every single networking issue individually and come up with hacks to get around them. And I decided that going back to the way that IOCs traditionally run, sitting on the local subnet with that they can contact the devices and the clients from, is actually the only way to be reliably sort all of these problems out. I hope that answers the question. I go into a little bit more detail on this in the paper that's associated with this presentation.
Okay, thank you. I have one last question before you go to the poster session. It's a cybersecurity question. It means, how do you manage patch management in these images? Because Ubuntu has to be patched a lot of times, and you have to reconstruct regularly your images. What do you do for patch management?
So this is a proof of concept, and I don't have a solution to that at present, but I expect that in future we would have an on-premise container cache, and that we would have processes for monitoring for vulnerabilities in that cache. And it's interesting because obviously many of the vulnerabilities, so we're based on Ubuntu, and vulnerabilities in Ubuntu don't necessarily mean that our container is vulnerable, because our container only runs a single process. And so it's only if it's using libraries from that are compromised that it's actually an issue. So the attack surface is smaller on containers, so it's worth remembering that as well.
Okay, thank you, Gilles. Alain, do you think we have another question, or can we close the session?
Yeah, we have to leave people of this poster session.
Yes.
So maybe
thank you, everybody.
Yes, thank you to all the participants, and see you at the poster session. Goodbye.
Bye-bye.